In this video, I'm focused on projectile motion. This is the 6th of 7 videos in my Unit 2, titled Kinematics. If you want to practice what is covered in this video, then check out the video description. You can find a link to my worksheet 2.06, as well as video answers for each problem. What is a projectile? There are 3 conditions. We are looking for an object that is in the air, that is moving both horizontally and vertically at the same time, and that is only acted on by the force of gravity. Here are 3 objects. They are all in the air. The question is, which one of them should be considered a projectile? Well, it would not be choice A. A commercial airliner has more forces acting on it than just the force of gravity. It would not be choice B. The rock is moving in the vertical plane, but not the horizontal plane, and that would be considered a freely falling object. The answer is choice C. Once the football leaves the quarterback's hand, it meets all 3 conditions on the left and is considered a projectile. Let's stick with the football being thrown by the quarterback. This football is thrown up and to the right with an angled initial velocity, and after it leaves the quarterback's hand, it will travel through the air with this parabolic or curving path. Because the football is thrown with an angled initial velocity, we can visualize the horizontal and vertical components of its velocity by making a triangle. Since the ball is moving in each of these dimensions at the same time, by breaking the velocity up into these components, we'll have an easier time analyzing the overall motion. Here, I am analyzing the vertical velocity of the football as it moves through 5 positions of its parabolic path. Position A is the release point. This object was thrown up and to the right, so part of that angled velocity is directed upward. That is the vector I'm copying at location A. The length of it is related to how fast the object is moving, and then obviously the direction says that the ball is moving upward at this location. The question is, what would the football's vertical velocity vectors look like at positions B, C, D, and E relative to the one that has already been drawn at A? At position B, this is still on the upward trajectory, but a little further along. I think the ball is still moving upward at this location, but not as fast as it was at A. When it gets to position C, which represents the peak of the parabola, the object is changing from moving upward to downward, and at this instant of time has no vertical velocity at all. Position D is on the downward side of the parabola. The object is beginning to move downward, and at position E, it is moving downward even faster. So this is what is happening. The projectile's vertical velocity is becoming more negative as time elapses. But why is this happening? Well, the projectile is acted on by a downward force of gravity. This causes a downward acceleration, and is the reason each velocity vector in the vertical plane becomes more negative as time goes on. Here I am analyzing the horizontal velocity of the football as it moves through the same 5 positions. Because the object was thrown up and to the right, some of that is directed to the right. That is the vector I'm copying at position A, the initial velocity in the x-axis or horizontal dimension. Question is the same. What would the football's horizontal velocity vectors look like at positions B, C, D, and E? Well, I think they will all be constant. I expect the football to move in the same direction and with the same velocity the whole time. And the reason is because the only force acting on the projectile would be a downward force of gravity. That will affect the vertical motion of the projectile, but not the horizontal motion. We would need a rightward force to speed these vectors up. We would need a leftward force to slow these down. We don't have either of those, so I expect the football to move with a constant horizontal velocity throughout its entire flight. Here is a summary of the previous 2 charts now combined into one. The overall motion of a projectile can be complicated to analyze, but breaking them up into their horizontal and vertical planes will make them much easier. In the vertical dimension, the projectile is accelerating due to gravity. It is a freely falling object. In the horizontal plane, the projectile moves with a constant velocity, and these 2 are happening at the same time. Let's talk through an example problem where the goal is to relate the horizontal and vertical velocities of a projectile. Imagine you are driving in your car at a steady or constant velocity while holding an object. If you were to toss the object straight up into the air, as shown in the image, the question is, where would it land? Would it land behind the driver, near the rear windshield? Would it land right back in the driver's hand? Or would it land in front of you, near the front windshield? Well, the first thing to point out is that at the time of release, both the driver and the object are moving to the right with the same horizontal velocity. And that is because the car, the person, and the object are all initially connected, so they are all moving together with this velocity vector to the right, labeled as v car. Well, the person has thrown the object straight upward, so they have certainly changed the vertical velocity of the object, but notice that the person has not thrown the object forward or backward, and therefore there is no reason that the object would change its horizontal velocity. So whatever it had at the time of the throw, v car, it should maintain throughout its flight. Well, the car itself is moving at a constant velocity. That means the driver in the car is doing that as well. We've discussed that there's no reason for the object to change its horizontal velocity, which is equal to the car. So that would mean that the object would land right back in the person's hand, and that would make the answer choice B. So this problem serves as a good example of why it is best to analyze a projectile's horizontal and vertical motion separately, as they are independent of one another. Let's talk about equations. I think projectile motion questions can be solved with 4 equations. They are all on your screen. Horizontally, we have already discussed that the object moves with a constant velocity, so I'm referencing a constant velocity equation. Vertically, the object is accelerating due to gravity, so I'm listing the 3 kinematic equations for accelerated motion. Projectile motion questions can be challenging, and one of the reasons is that there are many variables you may need to analyze. I will recommend that you start with a list that looks like this. In the horizontal dimension, we have a constant velocity. There are only 3 variables mixed in to the previously mentioned constant velocity equation. In the vertical dimension, we have a more complicated accelerated motion, and therefore there are more variables to analyze. I'm showing the 6 variables that were mixed in to the kinematic equations on the previous slide. I am also adding in the x and the y on the side of the list because I have seen many students get confused, being that there are multiple x-related variables and multiple v-related variables. So the x and the y will help you differentiate between which variables are horizontal and which variables are vertical. Now it looks like a daunting list with 9 total variables, but as long as the projectile is moving near Earth, which most of them will be, we already know the acceleration value, and there are 2 time variables in the list. If we have one of them, we have both. Let's look at an example. The goal is to identify given information in this problem statement, and then place that information in the correct place in the list. Here we have a soccer ball that is being kicked. We are given information for the ball's velocity after the kick in terms of its magnitude and direction. Now the first thing I see is that this kick is likely taking place on Earth, and therefore I would plug in negative 9.8 meters per second squared for acceleration. Also, in the y-axis plane, the x0 variable represents the initial height of the ball. I'll set the ground as a height of 0 meters, and I'll put that next to the xo variable. Next, let's look at the 20 meters per second piece of given information. This is stated as a velocity, and it has the units of meters per second, which is another giveaway that it will be related to one of the 3 velocity-related variables in the list. But where would we put this 20 meters per second? Well, the answer would be that it wouldn't go in for any of these 3 velocity variables. The first one is related to the x-axis. The next 2 are related to the y-axis. Well, this is an angled velocity. It has parts in both the x and y dimensions. And as mentioned earlier, if you see an angled velocity, then you'll likely want to make a triangle and analyze the horizontal and vertical components. And these are the values that will go in the list. From there, let's get the numbers involved. The overall velocity, or the hypotenuse of this triangle, is 20 meters per second, and the angle is given as 30 degrees above horizontal. So I now have the information necessary to perform the trigonometry to find the 2 components, and these are the answers after making those calculations. Now observe that the initial vertical velocity is directed upward, and therefore positive 10 meters per second would be a good selection. But later, you may solve a problem where there's an object starting up in the air. Maybe someone is throwing something from the top of a building, and maybe they're throwing it down at an angle, below horizontal. Well, trigonometry will not produce negative numbers, so you would have to recognize to make this a negative value as you plug it back into your list. Now we can go back to the list and put those velocity components in their respective places. Looking back at the problem statement, there is no question being asked here, but we can talk about potential questions that could be asked, and therefore, which variable to put our focus on. Maybe the question asks, how far will the ball travel before it strikes the ground? We would be looking for the change of position in the x-axis plane. Maybe the question is, how long will it be in the air? And that would mean we want to focus on the time variable, and it doesn't matter which of these we solve for, since they are the same. Maybe the question is, how high will it climb? Well, now we're looking for the final position or final height in the vertical plane. In any question of how fast is it moving after the kick, we'll want to find the vertical velocity in the vertical plane, as that is the one that is changing throughout the flight. Let's look at a second example. Here we are given numerical information, and now a specific question is being asked. We have a cannonball that is being fired horizontally from a given height and with a given speed, and the question is, how long will it take for the ball to reach the ground? To get started, let's see if we can organize the given information into our list. The first thing I see is that there is no statement regarding this taking place anywhere other than Earth, so I will again make my acceleration negative 9.8 meters per second squared. In terms of the vertical plane, I'll set the ground as a height of 0 meters, and that would mean that the ball is being launched from a starting height of 50 meters above that point. So my initial vertical position is 50, and my final vertical position is 0. Let's look at the launch point. Observe that the ball is being fired entirely along the x-axis, since it is stated to be fired horizontally. That means all 80 meters per second that we're given are in the velocity for the horizontal plane, and that would be none of the initial velocity is directed in the vertical plane initially, because this object was not fired up or down. From there, we focus on the question. It says how long, that is a question of time, and I can solve for either of these two time variables. But look where we have more information. I have 4 pieces of given information in the y-axis list, so I'm going to put my focus there. Zooming in on that point, I want to pick the right equation. I'm focused on the fact that I have no information for final velocity. I don't know it, I'm not looking for it, and therefore I would pick the second of these 3 options, as that avoids the final velocity variable. Now I just need to plug in the list's given information, perform the algebra, and I'll get the final answer as 3.2 seconds. One final example here, and I won't solve through the whole problem, but there's a couple things that I want to point out for more challenging questions. Here we have a student throwing a ball with an angled velocity, but now it is starting at a height above the ground and moving through its parabolic path until it strikes the ground again. We are also being asked 2 different questions. Question A, can we find the maximum height reached by the ball? And then question B, how far does the ball travel horizontally before striking the ground? For question A, we are looking for the maximum height, so we would want to create a list of variables from the throw point until it reaches its maximum height. That would be the important time frame to analyze. Question B asks how far does it travel before striking the ground. So now we would want to create a list of variables from the throw point all the way to the end of the projectile's flight path. So multi-part questions can be challenging, not only because we have to solve for multiple things, but also because we might have to make multiple lists of variables for each of the important time frames. At this point, if you want to pause the video and try to fill out these 2 lists yourself, feel free to do so, and then resume when you're ready. I'll talk you through each of them in a minute. Let's start with the list from the throw point to the maximum height. Here are all the pieces of information that we should know, and I've put a question mark next to the variable that we want to solve for. The velocity information would come from making a triangle with the angled 8 meter per second velocity and the 30-degree angle. The starting height is 1.5 meters above the ground. The object is reaching its maximum height, and that would mean it is not moving vertically up or down at that point, and this throw is taking place near Earth, so we know the acceleration. Being that I am solving for the maximum height, let's find the final vertical position of the object. Next, from the throw to the ground, some of the variables from the previous list we can copy right over, but not all of them. I think the velocity components are the same. The person threw it in the same way. I also think the starting height of the object is the same, as well as the acceleration due to gravity. The difference is that now we are not solving for the final position, we are solving for the horizontal displacement, so the question mark is moved, and instead of not knowing the final position vertically of the object, we now know it ends at the ground, so the final position has changed to 0. Lastly, we previously knew its final velocity was 0 because it was at the maximum height or the peak, and now that it's hitting the ground, it will be moving downward in the vertical plane with some negative number, and we don't know what that is, so I'll leave that blank. From here, we would want to use these lists to solve the two problems. I think it's a little lengthy to do in this video, so I'm just putting the answers on your screen if you care to complete the work on your own. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.